Okay, so again for our session norms, welcome everyone. So we ask everyone to please engage actively, be open, ask away, and let's give each other our undivided attention for this session. So just fun-filled 2 months actually, right? We started on October 18, and now it's November 25, and at first we were nervous if people are gonna join. But yeah, we're very happy, and hopefully you two are happy, and marami kayong natutunan on quantum and quantum technologies as well. So as you might have seen on our social media channels, no, if di nyo nakikita, follow us on Facebook, LinkedIn, no. Pero yeah, we had the hackathon na no last Monday. No, the team was there in Cebu, and yeah, it was so much fun and so much excitement. Ang nadama ng bawat isa. We had a great time doing that, and yes, we're very excited to do it again next year or kung kailan mapag-uusapan. Pero yeah, don't worry guys. This might be the last lecture for now. For now, ha. Pero yeah, we're very happy for kung ano ang nangyari last time, and yeah, we were very hopeful sa season 2. Wow, season 2 for this program. Hey, some reminders if or anything else for your homework. Homework 3 is still open. No, thank you for those that are continuing to answer your homeworks. You have 3 attempts for the homework. You can try again. No, you can submit again, but response editing is disabled. Yeah, you can still try to answer after those first 3, but of course, the highest score of those first 3 would only be recorded. And your homework 4, the final homework would be posted on Monday. And about the certificates, this would be discussed at the end of the lecture. What are your requirements for this? Okay, all right. So we'll just offload it, all of the announcements later at the end. So at this point, let's get straight to the first session of this lecture 6. So I would like to give the floor now to Sir Bobby Corpus. Hello po, sir. Good afternoon.
Hello guys, good afternoon. Di lang ako magpapakita kasi actually I have some cough and cold and it doesn't look nice. So I will just hide my face. Okay, so let me now share my screen. Uh, Let me share. Okay, ito na lang. An app, no? Sa photography. Can you, okay? I think you can see my screen now, no? Yeah, so this is actually one of the most, this is a very important topic now because um, this is like a poster child of quantum computing, no? The quantum cryptography or the the application of quantum computing into cryptography. So when Peter Shor was invented his algorithm to crack the RSA encryption, suddenly there was a lot of interest again in the quantum computing research, and the thing about this, no, is it's a real threat, no, it's a real threat into our crypto system, no? So um people or companies, no, big companies, nation states, no, are not just creating quantum computers, no, just for what you call this, applying it to other problems, no, but the most important, um really the most important thing is that they are trying, no, they're trying to be able to be the first one, no, to create a quantum computer so that they can decrypt the messages that have already been stored, no? So they just get these messages no? That are encrypted, and this and they don't have any way to decrypt them, no. So they just stay encrypted, but they get them, store them, that hopefully in the future a quantum computer will be able to decrypt the secrets, no, that are contained in these packets of encrypted data. So that's the importance of cryptography in quantum computing. Now there are actually three topics that I wanted to cover today, but the thing is we only have so much time and I'm only allotted 50 minutes. So I wanted to talk about quantum key distribution, and then I wanted to talk about RSA and Shor's algorithm, and also post-quantum cryptography. But the RSA and RSA and Shor's algorithm is a very long topic now, so I will not discuss that, but it's in my slide. And but I will discuss the quantum key distribution along, and if we have more time, I will discuss the post quantum cryptography now. Okay, so let's start. Okay, first let's review some relevant mathematics now. Okay, so suppose you have a photon, no? So a photon is a uh quantum mechanical particle, no, that has a state, no. And suppose the state is symbolized by this up down arrow, no. Up down arrow, it's actually called the polarization, no? Polarization of the photon, which is also the state zero, no. And then we have a basis, no. So the basis is itong up down and left to right arrow, no. These are mutually orthogonal, no, to each other, no. So if this is zero, then this is one. Okay, so which means a photon can be in a superposition between these two, no. Or if the photon is already in this state, then if you measure the photon, the polarization of the photon, then it is 100%, no, that you will measure this state. However, if your photon is in this state, but you measure it in a different basis, no. So for example, you tilt your measuring device into some 45-degree angle, no. And what will happen is that the basis that you are measuring is ito na, no. You'll measure this in this basis and this basis, no? So this one is diagonal, this one is anti-diagonal, no, and defined in terms of this, no. So it's very familiar notation, no. You must have already you must be very familiar with the Hadamard already, no. So it looks like this. Now the question is, if I measure this, the state up down, using this basis, no, using a device that is tilted at 45 degrees, what is the probability that I will get a diagonal, no? This one is the anti-diagonal. What is the probability? So this is the this is the the thing that we're going to use later in the quantum key distribution. Okay, so the mathematics is like this now. First, since we have this basis now, this basis can actually be represented as a linear combination of these two bases. Okay, and it's very simple, no, to derive the expression, this one here, no. To derive this one here is very easy, no. You just have to add them. When you add equation 1 and 2, this is plus and this is minus, this thing here will disappear, no. And this thing here will be times 2, no. 2 of this over square root of 2, no. And then if you simplify and if you extract, no, this one here, which is what you're trying to find, no, what you're trying to find in terms of the diagonal basis, then you will see that the up-down vector is just a superposition of the diagonal and the anti-diagonal. No? So which means if you measure a photon in that a photon that is that has a state of up down, if you measure it in a device that is oriented at 45 degrees, then there is a probability, because it is a superposition, then there is a 0.5 probability that you get this, and also a 0.5 probability that you get this. No? So it's like tossing a coin, no? Either get a head or a tail. So that's what happens if you measure this basis or this vector in a different basis. Okay, but if you actually measure it in the up down left right basis, then since this is already in the up down, 100% probability you'll get this, no? So yun, no? So after you measure this one, and you probably, for example, you get this, the state of the vector, the state of the photon, in terms of polarization, will become this one here. Okay? So it will change. Huh? It will collapse the state vector into this new state. Okay. In the same way, no, if I want to measure the probability, the probability of getting a so for example, if I have this, no, left right state, and I want to measure this in the diagonal basis, then in order for me to know what will happen, no, if I measure it, I will have to express this in terms of the new basis. And here you can see that it's also the same, no, except that there is a phase difference, no. But when you measure it, it's either this one here or this one here, no, what you'll get. No, so it's quite confusing, the arrows, no. Okay. Now this one is also needed, no. It's a just-in-time mathematics, no. So a Bernoulli trial. Suppose you have a coin, no, a coin. There are only two possibilities, no, success or failure, no, head or tail, no. And there's a probability of getting a successful, so the probability P, let P be the probability that you get a success, no, or a head, no. Then by independence, no, so two different Bernoulli trials, no, they will be independent of each other. And also, if P is the probability of success, then 1 minus P is the probability of failure, no? So that's quite straightforward, no? But what happens if, but this is just one trial, no? So one flip of a coin, no? And then you get either a head or a tail, no? With probability 0.5, no? For example. But what happens if you flip, no, the coin many times, no? And you want to compute for the probability that you have n successes, no, or n failures, no. So this is where the so we give an example for that now. So in this example, I tailor it to the so there is an adversary, no. So someone is trying to steal your secret, no, and then the probability of them not detected by you, no. So, and the probability that they are not detected is 3/4. Okay, for every transmission that you make, they are going to, there's a probability of 1/4 that they will be detected, or 3/4 that they will not be detected. Now the question is, what is the probability of them being detected, no, at least once, being detected at least once? Okay, so if they are not detected 3/4, so since for every transmission, there's a probability that they will not be detected 3/4 of the time. If you have n of these transmissions, then there is a probability that they will not be detected at all in n of these transmissions. And that probability is 3/4 raised to the n. 3/4 raised to the n. However, since we are trying to catch them, we want to we want to we want to determine. Kasi we can catch them because there is still a probability, no, that they will be caught, which is actually I don't know. So we want to be able to know ano probability for us to be able to catch them, no? How many times do we have to repeat the experiment, and how? So for assuming each experiment they actually tamper with your communication, no? They're actually eavesdropping for every experiment, for every transmission. So what's the probability that you are gonna catch them? No, you will be able to detect them at least once, no, once or more, no. And the probability is just this, no, 1 minus 3 to the 4 over n. So that's the probability of catching an eavesdropper. Okay, now let's now go to cryptography. That's the basic mathematics that we need, no, in order to talk about quantum key distribution. So cryptography is actually in simple terms, no, it is scrambling a piece of information so that no one except your trusted person can read that, no. And there are two ways to do that. One way is called the symmetric key cryptography. So which means there is a key that you have to agree with each other, no? And this key is used in both encryption and decryption. Tapos meron naman tinatawag na asymmetric or public key cryptography, no? This means that there is a public key that you can advertise, no, to the world, no? You can put it in your LinkedIn, put it in your Facebook, no, because it's a way for them to send you encrypted messages, no, so that only you can read it, no. And then the private key is the one that is used to decrypt the message, no, that was encrypted by the public key. Okay, so that's why it's called asymmetric, no, because there's one that is public and the other one that is private. And an example of asymmetric encryption are itong RSA, no, which is what we use many times, no, in our in I mean, if you open a browser, no, and you take a look at the what you call this lock button, then you can see it's either a RSA, no, uh, Rives Shamir Adelman, or the other one, which is elliptic curve cryptography, no, which we are not going to discuss. But in lecture series number 2, this was the lecture series number 1, diba? Lecture series number 2, we will deep dive into that. So you know, symmetric and asymmetric encryption. Okay. Now, is there such a thing as an unbreakable encryption? That no matter how powerful your opponent is, no matter how algorithmically sophisticated, how powerful their computing is, no, and how mathematically gifted they are, no, is there such a thing as a unbreakable encryption? Yeah, well, there is such a thing, no. It's called the one-time pad crypto system, invented by G.S. Vernon, no, Vernon of AT&T. So this is probably secure, no. There's a mathematics that prove that this is secure, because no matter how much you try to break it, to get a pattern out of it, you cannot. Okay, so it's impossible to actually get a pattern and be able to break this, no? And the reason for that is every piece of information that every letter, no, every letter that you encrypt is using a different key. But the only time, of course, that but there is a loophole here, no? If the random number generator is not random, then it's possible that a mathematically gifted person, no, or sophistically uh, computationally powerful adversary can determine the period of your pseudo random number. Or if someone is able to get your private key, no? So someone steals it from you physically, no? Then yeah, that's the, and also the third one is you actually reused your private key, no? You cannot reuse your private key in this case, no? Only once, kaya one time, eh? Okay? Because of that, it's unconditionally secure, no? Unbreakable. But the only problem with this encryption is that since every key is different for every message, no, that you send, if you want to send another message, then you have to create another key, no? So what you can do here is you can create a set of keys, many of them, no, so many of them, and then you meet with your guy or girl, no, or whatever, and then you exchange this, no, and then every time you send a message, you will just go through the list of keys, no, that you send. However, there will come a time that you will exhaust all of your keys, no, and that's the problem, no. Ideally, you should never meet with your counterpart, no. And so ibig sabihin, with this the problem with this encryption is that it needs the key distribution is a big problem. But before I get ahead of myself, no, let me just tell you what a one-time. Let me just describe what a one-time key crypto system is, no. First thing is you have to define your alphabet, no. So ito yun, no, ABC, capital ABC, and then you have here your numbers, and then some of the punctuations that you use, no, and then you have a space, and then you map them to numbers, no. So in order for us to be, I know, consistent, no. So for example, since the largest string here number is two digits, no. So kapag 0 less than 10, we just pad it to the 0, no. Pad it to the 0. Okay. Then next, you create a private key, no. This is an example, no. And there have to be many of these, no. And this one has to be shared with your counterpart, no. And then prepare a message, no. Like for example, my pin is 1234. That's the message that you want to send to your friend. So map your letter, no, letter M. Map it here. Where's letter M? Where's letter M? Oh, 38, no? And then letter Y, no? Letter Y is here. 24, no? So at the end of that mapping, you will get you will get an array of number, no? An array of numbers. So for each of these numbers that you got, you will encrypt them, no? And the formula of the encryption is like this: the number, and then you add it to the key. So for example, if I'm encrypting the first, which is 0, no, I equals 0. So the first is the first digit, sorry, the first message that is turned into a number plus the first element of the key, no? So ibig sabihin 30. 30. What is the first message? Letter M. Letter M is M. Sorry, big M, no? Big M is 38, no? So 38 plus 30, and then you get the remainder, no? When you divide it by L, where L is the number of the alphabet, no? It's the length of the alphabet, no? So in this case, I already counted this. This is actually 76, no? And then when your friend, no, or your colleague is able to get this message, the decryption is very easy, no? So since symmetric encryption though, it also uses the same key, but it will, so to get the message, you just when you get this, you subtract it by the key, which is this one here, key 30, and then you add the length of the alphabet, this is 76, and then get the modulo, and then you'll get your number, get your message. No? So do it for all of it, and then eventually you will get this one here. Okay, so this is actually an example I got. No? So meron kang, my pin number is 1234. You map it with the with numbers, no? So 38, 24, no? And then here 1, 4. Okay, so meron ding mga less than 1 digit, no? So I just remove the padding because these are already numbers. These are not strings anymore, no? And I have to use a formula for them. Okay. So I do that to get a 68. So if I do that for every number here, this is the actual ciphertext, no? Okay. So we call the scrambled text a ciphertext. So it's a encrypted text. So ciphertext is also the same as an encrypted text. Okay. So sinabi ko na to kanina, no, sa considerations of a one-time pad. So one-time pad is really unbreakable, no? But you really have to have a truly random generated bits now. Keys cannot be reused. And ito lang now, this is the problem. How do you distribute the keys, no? Because every key that you create, because you cannot reuse keys, you have to generate a set of keys, no? So how do you do that? Either you meet with the person and give the key, so allow the keys already, or you can use what is known as a quantum key distribution, QKD. So yung QKD is a mechanism, no, that uses the mechanism of quantum theory. No? So with quantum theory, we know that whenever there's a measurement that is that is when a system is measured, no, it will potentially perturb the system, no, and which makes it change in state, no. But there are also times that it doesn't change, no? And we will see that later. There are also many protocols in in quantum key distribution, but this one is the earliest and also the simplest, no, to explain. And it uses the quantum property of polarization. So we polarize photons, which I'll explain later. So when you have a light, no, actually we polarization is something that we already are very familiar with, no? Especially if you have heard of the Polaroid camera, no, that's the one which when you take a picture, no, it's a picture of a polarized image, no. Another thing is when you have a some of your, for example, sunglasses, no, they are capable of polarizing light, no, because light naturally has the different polarizations, no, and because of that, there's a glare, no, and if you want to minimize glare, you have to filter only a subset of that, no. So when you filter a subset, that's you use a polarizer. There are different kinds of polarization. There's a linear, circular, elliptical, no. When when electromagnetic kasi, so when an electromagnetic, I'll go here, no. An electromagnetic wave, no, is composed of a electric and magnetic wave, no, that propagate through a certain direction, like this one here, and they oscillate perpendicular to each other, no? But we don't care about the magnetic wave for this component, no? We only care about the uh, this electro wave. No? So, for example, here you will see that the uh, the electric wave only oscillates, no, in this plane, no, only one plane, no. So that's what that. So when that's the case, no, it will appear to be going up, going down. Okay, so it's like that, no. It's a linear. So the projection of the oscillation, no, in this what you call this in this plane is a line, no? However, so the circular polarization is the electric wave, no? It actually in the direction of the propagation, it actually rotates, no? Rotates. So when you get the projection of that into this plane here, no, you'll get you will trace a circle. Dito you'll trace a line, no? Dito you'll trace a circle. And this one is more general, no? If if the components, no, have different what you call this magnitude, then you will naturally get a elliptical curve, no? So for example, here the components in this axis has the same magnitude as in this axis, so it becomes circular. Okay, but for the purposes of our quantum key distribution, we are only going to focus on the linear polarization. So we need a polarizer, no? So a polarizer is a device so that uh, when you transmit a single photon, no? So there's such a thing as a single photon gun, no? So it transmits only one photon at a time, no? So if you transmit one photon, then so the photon already is already let's say is what you call this is polarized in a certain direction. Now, if you have a polarizer and the polarizer has the same direction, no, as the as the polarization of the photon, it will allow the photon to pass through 100%. Now, if you tilt your polarizer, no, in such a way that it is 90 degrees from the polarization of the photon, what will happen is that the photon will not go through, no? It will either be absorbed or reflected. However, if you tilt your polarizer in 45 degrees, for example, no? Now the photon, which is polarized up down, it actually has components in the diagonal direction, no? So you can resolve that components. We did that already, no? We did that earlier, no? When we did this, no? Yung ginawa natin, no? When we did this is what we did, no? So we determined the components of that photon that is in the up-down direction as a in terms of the diagonal direction, no? So in that case, there is a 50% chance na there's a 50% chance na your photon will go through, no? But its state vector will collapse, no? Into one of the components, no? Either the diagonal or the anti-diagonal components, no? So let's take a look at this, no? A photon polarized at the up-down, no? Vertically. or horizontally. Tapos a photon that is polarized vertically can pass through the polarizer and can be in one of two states. No? Kapag ito, it will pass through the polarizer. It will either be, it will emerge, no, as this polarization, or this polarization here. No? So in other words, the state vector, the wave function of describing the polarization has collapsed into one of these 50% probability. Now, this is now the description of the Bennett and Brazard protocol. So we have two characters. Now in cryptography, there are two. Well, actually there are three characters now that are well known. No? Alice and Bob and Eve. No, Alice and Bob, they are the people who communicate with each other, and Alice is the one that eavesdrops. No, so Eve is the one that's the eavesdropper. Anyway, so Alice and Bob, they need to communicate with each other, no, securely. But before they can do that, they need to agree on a encryption key. And the way for them to communicate the encryption key with each other is by using the polarization of photons. No? So ito yung protocol. Number one, Alice will first sandali lang. This is not yet the no. So let me just read this. Alice will send polarized photons. No, so this is the setup. No, the setup. I'll describe the setup. So that the Alice has two different polarizers. No, one that polarizes a photon in the up down or left right direction, which is this one here, or in the diagonal direction. No, diagonal, anti-diagonal direction. So meron siyang dalawang ways to do it. No. Now, they agree. Okay, so Alice and Bob, they agree. If Alice will need to send a 0, then she can either send a up down or a diagonal. No? So she can either send this or this. Okay? Yan yung agreement nila. No? If Alice wants to send a 1, then so 1 is the value of the bit. No? She will send a photon that is polarized in the left-right direction or in the anti-diagonal direction. Okay, so remember this, guys, no? Up, down, diagonal, left, right, anti-diagonal for 0. Now, this is now the protocol. No? First, Alice will have to get hold of a truly random generator that will generate random bits. No? So meron kang sequences of zeros and ones, no? 1, 0, 0, 0, 0, 0, 1, no? So it's a random, no? And then she will then, now for example, suppose nakakuha siya ng 0, no? So if she gets a 0, then she will have to encode that information into either this one or this one, no? Okay. So either ito yung gagamitin niya or ito yung gagamitin niya. And then she will take note what basis, no? What kind of basis she used in order to polarize those photons, no? She will take note. Next, Bob receives the photons, no? And then si Bob naman, he has the same polarizers, no? The one that can measure in the up-down direction, up-down left-right direction, and one that can measure in the diagonal direction. No? Pero he will have to choose randomly, no? He will have to choose randomly. He cannot guess, no? He cannot guess kung ano yung in what direction, in what basis that Alice sent the photo, no? So he can only choose randomly, no? Either this one or this one. And then he will take note of the basis that he used, no? So he will take note na, oh, this is the one that I used. Oh, this is the one that I use for this, okay? So, there are two cases kasi, no? If Alice sent a photon in this state, no, what is this? This is the zero, di ba? Zero. Kapag zero yung bit mo, yeah, you can send this, no? And Bob measures it in the basis in the same, no? Nag-match yung kanilang basis na ginamit, no? Then what will happen is that definitely Bob will measure the same state, no? Since Bob measures the same state, malalaman ni Bob na, okay, uh, Bob can get the value zero. But by the way, Bob doesn't know, no? Bob doesn't know that they no at this point in time, no, Bob doesn't know that he was using the same basis as Alice, no? So kung ano lang yung nakuha niya, i-record niya, no? I-record niya. So he will measure this with a probability of 1 and records the value 0, no? So 0 is the value of the bit, no? Because this one corresponds to 0. Okay. Now Bob measures. Now, what if Bob uses a different measuring device, no? Which is measuring in the diagonal. What will happen? Then he will get, we computed earlier, di ba? Kapag ito yung pinadala mo, then you will get a 50% chance of getting this one or this one, no? Now, whatever Bob gets, no, it's either this one or this one, he will have to record it, no? So if he gets this one, he record a value of 0. If he measures this one, he will get a value of 1, no? So if you take a look, no, he will only be correct even if he chooses the wrong basis. He will still be correct 50% of the time, no? Okay, so if Bob uses the wrong basis, he will be wrong with a probability of 50%. No? Now, okay, so assuming na tapos na, no? So they already sent all of their bits, no? And then Bob already measured everything. The next thing that they will do is for Alice to tell Bob the basis that she used in sending all of those photons, no? Hey Bob, I used this basis, no? I used the up down. Hey Bob, here's the diagonal. Okay, so for every one of those photons, no, that she gave, she will tell Bob what basis. So what Bob will do is keep all those. So he will check, no, ano yung mga basis that na nagmatch sila, no? What basis did I use that match with the basis that Alice used, and only keep those, no? The rest I will throw them because I'm sure that 50% of them are wrong, no? So now, if Bob keeps all of those data where the basis matched with that of Alice, then he is sure that he was able to get that whatever bit value Alice sent will also be the bit value that he will send. No? Assuming no one is listening. No? Now, here's the part, no? They will have to determine if someone is actually listening, no? And how will they do that? They will do it like this, no? Okay, Bob. So what they will do is they will select a subset, no, of those that they have kept already, no. Those that nagmatch, they will just select a subset of that, no. And publicly, no. Publicly, I mean, anyone can just eavesdrop, no. But they are actually communicating. Alice will say, like for example, Bob, for this first bit, I actually sent you a 0. And Bob will then say, oh, I also got a 0. Okay? So they will select a subset of the qubits, no? Para they will compare. Now, this is the catch, no? If someone was actually listening, one of those qubits, one of those bits will be wrong. Okay? One of those bits will be wrong because Alice, when she was, sorry, when Eve, when she was eavesdropping, she, what happened was that when she eavesdropped, no, she measured, the photon polarization that Alice sent, no, and then she recorded it. But the thing is, when she measured, she also doesn't know, no, whether Alice was using up down basis or diagonal basis, no. So she will have to guess also, no. So now the next slide will tell us how, ano yung probability that we can catch ano si Alice, no? So no, an eavesdropper by the name of Eve, no? So what happens is that she measures the photon sent by Alice, and then also randomly, no? Randomly, she will choose this one or this one. And whatever she has measured, she will send it to Bob. Okay? Now, if measured the photon in the same basis that matches that of Alice, then she will measure the correct bit value. And also the photon will be in the same state that she will when she forwards it to Bob. No? So nothing happened. No? Bob can still will still be able to measure the same polarization that was sent originally by Alice. No? However, if she measured it using a different basis, so the probability of her getting the correct value is 0.5, no? 0.5 na lang, no? Because it was the wrong basis. And what happens is not only that, no? She also altered the state of the photon when she forwards it now to Bob. Okay? So Bob actually doesn't know the existence of Eve, no? He's just happily getting the photons from Alice without knowing about Eve, no? And then when he gets this photon from Eve that was already perturbed, no? That was already disturbed, he also has a probability of measuring uh measuring the state of correctly na 0.5, no? Kasi posible na when Alice sent this, and Eve measured in this basis, but she got this diagonal here and this up down here, they have the same bit value, 0, di ba? They agreed beforehand that if I get this or I get this, 0 yan, no? So but when Bob will also measure, there will also be a probability that he'll get the correct value of, will he get this, but which is the correct value, but he'll also get this, no? There's a probability he'll get the wrong value. So in other words, for every bit, no, that was transmitted by Alice, the probability of the probability of Eve getting detected, no, is first the probability of her measuring in the wrong basis, no? The probability of measuring the wrong basis is now time to drink water. 0.5, no? Now when that photon went to Bob, the probability of Bob also measuring the wrong bit is also 0.5. Since these are independent events, no? The probability of, so ibig sabihin, this one here, the probability that you will catch Eve, no? Because you found out that the bit is different, no? Even though Alice sent it in the basis, in the same basis that you measured, but you found you got a different bit value than her. That already uh, tells you that someone is listening, no? Now, what are we trying to do here, no? We are trying to determine how lucky Eve will be, no? Na hindi talaga siya madidetect in any way, no? How lucky will she be? No? What's the probability of her luck, no? So, the probability that she will not be detected actually is 3/4, no? For 1 bit value. Okay? 1 bit value. Now ngayon, as we have discussed earlier, if you send more than 1 bit, no? Let us say big letter N, no? N can be as many as you want, no? Actually, yung tanong dyan, how much bit will I, how many bits should Alice and myself, no? Kasi Bob nga ako, di ba? Alice and myself reveal to the public so that there is 90% chance that we can catch the eavesdropper. No? I mean, we can determine there is an eavesdropper. No? So the variable here now is n. No, how many times do we need? How many bits do we need to open in public in order to determine the presence of an eavesdropper? No, so ibig sabihin, if at least one of those bits have a different value that we expect, that's the time you can say, oh, there's an eavesdropper. Okay, so if you determine, let's go to the next. So ito na yun, no? If Alice and Bob sacrifice n bits, the probability of detecting Eve is 1 minus 3 to the 4th raised to the n. No? Ito yung kinalculate natin kanina. No? Then this probability approaches 1 as n increases. No? So yung tanong na ngayon, if I want a 90% probability of catching Eve, how many bits should I open? No? Now, according to this computation, you only need 8 bits, no, in order to have a 90% probability, no, that you will catch that there's a eavesdropper. 90% is a very big number. No? It's a very big probability. Okay. So this is now the everything that I have explained. Ito na yun, no? This is how you view it in diagrammatically. No? So here, Alice will choose. No, so first she will generate a random number, no, random bit, no, and then she will either choose this one or this one, no. So for example, here Alice sends a photon in this direction. Alice sends a photon in the diagonal direction. So this one is diagonal, anti-diagonal. This one is horizontal, no, left, right. This was up, down, up, no. So now take a look, guys. No, take a look at Bob. No, when Bob measures the qubits, measures the photons. He take a look at the times. Take a look at the times that he measured in the same basis. No, so for example, dito he measured the same basis. No, dito he measured the same basis. Dito measure the same basis. Here measure the same basis. And take a look. No, if Alice sent a 1, he gets a 1. Alice sent a 1, he gets a 1. No? So these bits match, no? So when Alice says, okay, these are the bases that I used. Okay, sorry. Bob tells Alice the bases Joyce to make, no? And then they will keep those, no? These are the things that they keep, no? Okay, naka-check, no? These are the things that they keep. Okay. And then from there, they will get a subset naman, no? In order to reveal to the public that these are the values of the bits. Okay. And then so Alice says, oh, I sent you a 0. So if there is no eavesdropper, every bit that Alice will tell Bob, it will match his own record. But if there was a eavesdropper, then at least one of those bits did not match. Okay? And there's a 90% chance that you can get a bit that did not match if you open to the public N of these, no, letter big N of these bits. Okay, so that's the quantum key distribution. Okay. Okay, so guys, no, so I don't have time anymore. My 15 minutes is already up, no. So yes, let me give the floor back to Jabez.
Awesome. Just a sec. Let me share my screen. Okay. Ayan. Okay, so thank you po, Sir Bob, for that very wonderful explanation on quantum key distribution. No, yeah, it's not just about computing and optimization. No, there's so much more about quantum technologies and materials even, diba? So yeah, Sir Bob mentioned ito sa cryptography and yeah, how this can shape the future, no, on kung paano natin ini-encrypt ang ating data. Okay. Yeah, very funny rin, 'di ba? Na si Alice and Bob. And yeah, very fitting kay Sir Bob. Okay, at this point, no, yeah, we won't have a break na muna since the next session is a chill one, I should say. No, the topic is not chill. It's about Dush Joe's algorithm. Pero yeah, it would be a hands-on demo, so it's a bit more interactive and a bit more stimulating, I should say. So for now, yeah, I would like to give the floor to our second session speaker, Lance Raquel. Hello, Lance.
Hello, thank you, Jabez, for that introduction. Jabez, can you share screen for me?
Yeah,
Kasi
sure.
my Zoom crashes every time I try to share screen,
Okay,
and
let me
also
open.
if I try to turn on my video. Eh,
Just a sec. There we there we go.
All right, so good evening, everyone. I'd like first to congratulate everyone that participated during the hackathon in CIT, and I'd like to congratulate everyone that participated as well, and for the winners as well. Congratulations. So today I'll be discussing Deutsch-Josa algorithm. Uh, it's it was supposed to be a last lecture, but there were a lot of problems with it, so I had to learn this one first. So anyway, proceeding with the next slide, please. So there's a particular problem that Deutsch-Josa came up with, for which quantum computers can solve very fast, but classical computers uh, would have an exponential time to solve this problem. So this is the problem, okay? So the problem is that the functions, um, I mean, we are given an oracle. This is a black box access to a particular function f. So with these guarantees, okay? So this function has a guarantee that it takes in n bits as input, and then the function will output a single bit. Could be either 0 or 1, all right? So with a guarantee that f of x is either constant or balanced, okay? What that means is we know that this function either outputs the same value for all inputs, or it's a balanced function, which means half of the inputs will output 0, and for the other half output, for the half inputs, it will output 1. Okay, so the problem to this, the solution to this problem is basically the goal of Deutsch and Joso wanted to the classical computer, or maybe a quantum let's say quantum computer na lang. So it's to figure out if f is constant or balanced, okay? Whether it's constant or balanced. All right. We know that it's one of the two, but we want to know with 100% certainty if it's constant or balanced. All right. So next slide, please. All right. For Oracle F, so we have this. So I told you that we are given an oracle or a black box access to this function f. So we don't know what that concrete function is, but we can give a set of inputs and get a set of problems, right? So this is for oracle. So if it's a classical oracle, it'll get it can take an n-bit input, and then we have here plus here the 1-bit input, and then it'll get an actual input x, such as the output of this function is embedded in this last 1 bit. Okay, so don't get confused. Okay, so n-bit input, and then the 1-bit input, then we get n-bit output, and then the 1-bit output. Okay, so basically the output will be x as such and y for f of x. Okay, so the last bit from the last bit we can check the output of the function embedded in the plan. Okay, so this is the way we set it up, because if it was discussed from the previous lecturers, we know that the quantum computers have reversible computation. Okay, so we want the quantum oracle to be reversible. So this is a natural way of doing it. Okay, so if it's a quantum computer, next slide please. Okay, it's ayan. So this is not classical, hindi ko na change. It's supposed to be quantum. So if it's a quantum computer, it takes n qubits plus 1 qubit as the input, and outputs n qubit output, and then 1 qubit. All right, so it's that simple, right? So the computation description is the same, except that it's a quantum module implementing it. All right, so all right, next slide please. So for the classical algorithm for Deutsch-Josa, so now let's look at this. What is the classical algorithm to solve this problem? Okay, and remember that we need to remember that I mentioned earlier that we need to find the correct answer with 100% certainty. So if we think about it, given the black box access to this function, we need to query more than half of the input space, okay, to say with certainty whether this function is constant or balanced. Okay, so we want to figure out whether this function outputs the same value for all inputs, or if it inputs like for half of the inputs output 0 and half of the inputs output 1. Okay, but given that we want to solve with 100% certainty, we have to query at least half of the inputs plus 1, okay? Because we might end up being unlucky and get, let's say for the first half of the inputs, that's 2 to the n minus 1 plus 1 that we query, we get the same output, okay? That doesn't say anything whether this function is constant or balanced, okay? So it's very confusing, right? A lot of inputs and outputs, 0 and 1, so just bear with it, okay? So we just need to, so basically, if we get the different output for the first to the n minus 1 inputs that we query, so to say, the answer with 100% certainty to predict whether it's a constant function or balanced function, we need to query at least 1 point more than 2 to the n minus 1. Okay. So next is we have the query complexity. So for the classical algorithm, it's exponential in input length n. Okay. So that's for the classical algorithm for Deutsch-Josa. Next slide, please. All right. So just to note, in the Deutsch-Josa algorithm, it predicts whether the function is constant or balanced in polynomial time, okay? In fact, just with constant queries to this oracle, we can predict, okay? So now let's see this. Let's see how it works. So in this slide, we can see the quantum algorithm in step 0, which is the input. Okay, so step 0 of the quantum algorithm. So basically, this is the input, okay, that we provide to the quantum algorithm. The n with n qubit part of the input, it's all zeros, okay? And the last qubit, which is 1, will take in the qubit 1, as simple as that, okay? Now, next slide, please. For the step 1. All right, that's step 2 now. For the step 2, this is supposed to be step 1. I'm sorry, I got confused. So for the step 1, we have the Hadamard transform of the quantum algorithm. Okay. So first is we need to apply the Hadamard transform. Okay, if you remember from the first few lectures, Hadamard gate is given by as follows. Okay, this one, 1 over root 2, 1, 1, 1 minus 1. Okay, so so in particular, this transfers the 0 state into the plus state. Okay, as you can see in the first qubit 0, we have a plus sign on the right hand side of the 0 plus 1. Okay, and then when you arrive to the second qubit, you get a 0 minus 1. All right, so and then yeah, all right, so basically it becomes a minus state. Okay, so if we now focus on the right hand side of this PowerPoint, we can notice that their difference, okay, the 0 and the 1. Okay, so it's just a sign. It's the 0 is plus and then the 1 is minus. Okay, so we know that the Hadamard transfers is a single qubit acting on a qubit, which is 0. Okay, so it transfers 0 to plus and 1 to minus. All right, so to abstract it out, in the bottom part, which we have the A, so the Hadamard acts on a gentle gate, okay? Gentle qubit A, okay? Gentle qubit A. So we can see that the first qubit, it's always like, it doesn't have any phases to say with, it. So for it to correspond, for corresponding qubit 0, there is minus 1 to the 0. And if the input is 0, it's again 0. But if it's input 1, it's minus 1. So we can generalize it and write it as -1 to the power a. Okay, this one, as you can see. Okay, in fact, we can bring these two together and it becomes this. Okay, it becomes that the lowermost part in the right hand side. So we can combine them together and say that the Hadamard, when supplied on a gentle qubit, gentle single qubit a, is -1 to the power a dot x, and then x. Okay, so just to see it again, when x is 0, it's -1 to the 0, which is that one, and if it's x, it's -1 to the dot, I'm sorry, -1 to the a dot, 1, which is a, and 1, which is the single qubit there that you can see. So basically, when Hadamard appears on a single qubit, we can easily see that it's written this way, this last part, okay, with the summation on it. Okay, so I'm not going to explain, but this generalizes even when Hadamard, let's say multiple Hadamards are played on, okay, multiple qubits. Okay, so next slide, please. All right, so for a multi-qubit gate, okay, multi-qubit input A, let's say n qubits, for instance. When Hadamard is applied on those, we get the same expression, -1 to the a dot x, where a dot x is the dot product between a and x. Okay, and then for all possible inputs x, and yeah, for all possible inputs x, which is the most right part. Okay, where in fact this is all right. So we can see in this figure, in the circuit that we have. So this will be this will serve as the first step of a quantum algorithm. Okay. So basically, this expression, we'll use it later, but the first step, it's easy to see because for the first register, so we have n qubits, all of them are zeros. So the input is let's try to ignore first on the first the one. So let's try to focus on the most top part. Okay, so in the first 10 qubits being what do you call this, all right, so let's focus on the first 10 qubits. So the first step, because we know that 1, when has a Hadamard, it becomes a minus. Okay, and also before the first a and qubits, when it's all zeros, it's just equal. Next slide. Ayan, here we can see it's just equal superposition of all possible states, because -1 to the a dot x is always 1. All right. Okay, so this is just simple. Okay, this is the step 1. Step 1 pa lang to. So we all have 0 input in the first register, and then we apply Hadamard, and then we get equal superposition of all possibilities. Okay, so the second step, next slide, please. All right, this is very interesting. Okay, I used a compose on this because I couldn't look for figures for it, so I tried improvising. So this is the phase kickback, where we will see in many quantum algorithms. Okay, so the starting point, let me explain what phase kickback is. So basically, the starting point for it is the CNOT gate. Okay, so CNOT, we know it's a 2-qubit gate. So it takes in, let's say, input x and y as 2 qubits, and the output is x and y plus x. Okay, so as we can see in the topmost, in the top left, we can see the CNOT 0, 0 is equals to 0, 0. Okay, so let's try to detail this. Okay, so so let's try to instantiate. Let's try to instantiate it. So let's say that 2 qubits, q0 and q1, where Q0 is the control and then our Q1 is our target. So this together is a C0 gate. Okay. So C0 when supplied on 0, 0. So let's say that 0 is Q0. Let's say that 0 is Q0, and then the first position is Q0 and second position is Q1. Okay. So C0 applied on 0, 0 is 0, 0. Okay. Then we have 0, 0, 1, and then it's equals to 0, 1. Since the control is 0, so the target remains unchanged. Okay. So, but when the control is 1, the target is flipped. So basically that's the property of the CNOT gate. Okay. But in this case, let's look at this in the right-hand side of this presentation. So let's try to look at this. Okay. So we can see that we applied two Hadamard gates before and after the CNOT gate. Okay. So when we work this out, the interesting thing that we will see is the CNOT gate attacks as if it's flipped. So the control and target gates are flipped if we have Hadamard applied before and after. So that is, if you can see in the left figure, the first figure, we can see that this is the CNOT appearing on the standard basis. Okay, and then the control target is normal. Okay, it's in Q1, and then the control is in Q1. The control is in Q1, and then the target is Q0. All right. So if we have CNOT in the Hadamard basis, then the effect of CNOT is this one. This is the one that displays the H dot CNOT dot H. So 0, 0 is equals to 0. So we can work it out, but if we try to work it out, we'll see that if we have a Hadamard CNOT, Hadamard, 0, 0 will still become 0, 0, but 0, 1 becomes, oh, I'm sorry, all right. This is supposed to be the second one, that one is supposed to be 1, 1. Okay, if applied on Hadamard before and after the CNOT, your 0, 1 will become 1, 1. Okay, so it's just a typographical error. I'm sorry. So if it's the second qubit is if the second qubit is the control, so since the second qubit is 1, the target gets flipped. So it's like this. Okay, so 1, 0 is still 1. Oh my god, I flipped it. Okay, so bali siya, guys. I'm sorry. The results here for the right-hand side, it's supposed to be the 1, 1 is supposed to be on the before the 0, 0, and then the 0, 1 is supposed to be on the in the 1, 1 part. Okay, so nabali siya. I'm sorry. So okay, so this is basically the starting point to see the notion of phase kickback. Okay, so let me say more explicitly the way of using phase. Okay, if we take out this Hadamard gate, okay, if we only have this first two Hadamard gates, if we were to take this after Hadamard gate, so essentially the standard base is converted into Hadamard basis by the time we apply it. By the time we apply it after we apply Hadamards before. Okay, the CNOT gate is applied where the CNOT is applied. So next slide, please. Okay, so let's try to look at this now. Okay, so these are the all possible inputs for Q0 and Q1. So let's see what the impact is. Okay, so C0, we know that like Hadamard of 0 is plus and Hadamard on 1 is minus. Okay, so C0 on plus plus gives us plus plus, but C0 on plus minus gives us minus minus. And then C naught on minus plus gives us minus plus. And then minus minus gives us a plus minus. So it's like if we have the second qubit as plus in the first one, I'm sorry, the first qubit remains unchanged. But if you have the second qubit as minus, the first qubit gets flipped in the harmonic basis. Okay, so it's a plus, then it becomes a minus, and minus becomes a plus. It's very confusing, right? Plus, minus, there are a lot of zeros and ones. So there are a lot of inputs and outputs. So this is what we have to deal with, okay? So similar to how we derived the expression of Hadamard in the first step, we'll now try to derive the expression similarly for this phase kickback. So this is what we call a phase kickback. So if we have the phase in the second qubit, then that gets kicked back to the first qubit. So basically, in general, we'll derive this expression, this C naught x minus is equal to minus 1 to the x. Okay, so we'll have this phase that gets kicked back, okay, in the first qubit. This one, this minus 1 to the x, okay? So we'll try deriving it, okay, in the next slide. All right, next slide, please. All right. All right. So xy minus, all right. So we know that C naught and xy is xy plus x. So what is C naught on x minus, right? So what is minus? Minus is 1 over the root 2. We get 0 minus, and then we get 1. Okay, the first unchanged, and then let's just try to, when we expanded this, okay, so basically, okay, so let's say C naught applied on 0 minus 1 is, we know from this expression, we know that 0 applied on 0 is 0 plus x because the control is x. Okay, so let's just say from the figure that we have earlier, the one that was the standard basis, let's just say that the q0 is x, and then q1 is minus. Okay, so basically uh uh okay, so 0 is 0 plus x because the control is x. Okay, minus 1 minus x, 1 plus x. So this is just a regular C naught gate applied. Okay, so if we look at this, the second one, throughout our expansion, the second one, we could see that 0 plus x minus 1 plus x can be simplified as minus 1 to the x, 0 minus 1. Okay, so this is because if x is 0, then it's essentially 0 minus 1. So this is it's unchanged. So but yeah, so it's unchanged. But if it's x, but if it's x, then it's 1. Then it's 1. Okay, so minus 1 plus 1 minus 0. Okay, so it's 1 minus 0, which can be written as minus 1 times 0 minus 1. So essentially, if x is the control, is 0, then there is no phase that comes up. Okay, there's no phase. But if it's a 1, then we have this. Okay, so just to avoid confusion, I'm in this part already. In the third line, where 1 over root 2 x minus 1x x minus 1 to the power of x, and then 0 minus 1. Okay, so if it's 1, then we have this term phase. That's minus 1 that comes up. Okay, but but this minus 1 to the x in the last line, this minus 1 to the x is a global phase. Okay, this this minus 1 to the x is a global phase. Okay, that can be applied to either the second qubit or the first qubit. All right. So basically, that's essentially the notion of phase kickback. All right. So even though we started with the C not gate and X is the control, but if we have the second qubit as the minus, uh, then there will be a global phase minus 1 to the X that comes up. All right. And that can also be kicked back to the first qubit and applied on the first qubit X. All right. So C naught of applied on X and minus will give us minus 1 to the X minus. All right. So basically, this is the expression that we derived. By intuition, actually, we can see that from the previous slides, we have the Hadamard applied before, and yeah, but this is the expression that comes up, right? So next slide, please. All right. So this is when try to visualize again the figure of our standard basis of the CNOT gate. Okay, so basically, when CNOT is applied to the first qubit, which is just X, but this can be more generalized. Okay, this is the generalized version of it, the lowermost part. Okay, so instead of a single qubit X, we have a multi-qubit control. Say that we have a function. Okay, just try to imagine that we have a function applied on it. So imagine also that we have the oracle. Okay, so we had uh, the X and X. We have both X here, X and X. So we have the I'm sorry, the Y is not here. All right. Okay, so I'm sorry, it's so harder to visualize without the oracle on it. Okay, just say that try to visualize the previous oracle that I've showed. We have the X and the Y. Okay, so um we have the Y on the bottom right, and then we have the X on the topmost. So all right, yan, ayan, okay, that one. All right, so basically that is the oracle that we have. Okay, so if the multi-qubit X, can you go back to the slide? Okay, and this multi-qubit X and minus gate is passed through our oracle. If it passes through our oracle, the phase kickback property ensures that ensures that we will get this output minus 1 to the f of x, okay, as a global phase. All right, and x and minus. All right, okay, so that's the second step of the phase kickback. All right, next slide, please. Okay, so this is the oracle that we applied, and the output uh of a step that we got as 1 over root 1, so equal to the superposition of all possible inputs. Okay, now if we now apply the oracle UF, we'll get this X. Okay, we'll get this X in the lower center part. Okay, so after the summation, we have their X, and then we have the arrow of F, and then one yan, that one. So we will get this global phase. Okay, so it's basically the phase kickback applied to it. Okay, so X will have x will have a minus 1 to the power f of x, okay? That one. So that's basically the second step. No further explanation for the math. So I'm trying to explain it very simply. So, all right. So let's move to the third step, which is again applying the Hadamard transform. So if we would recall, this equation was already shown earlier. Okay, so this is where we will use the general expression that we had derived for Hadamard transform, which said which says that if we have a Hadamard like n applied on n qubits, a is in qubit register. Let's say if we have if you apply uh if we apply a head amount of n qubits, we'll get this expression. Okay, summation over all possible x minus 1 to the power a dot x dot product between a and x. Okay, so this is what we'll get. All right, next slide please. All right, so this one. So now we have the state at the end of step 2. Okay, this is the step 3 already still had a word transform. So this state at the end of step 2, right? We have 1 over 2 over to the n. We have we have 1 over to the root 2 to the n summation over x minus 1 to the f of x. All right. So now we just applied a Hadamard gate in the previous expression for this. So each qubit x, so basically the x has the same thing as a. So earlier we said that a so basically this is x. So it changes the variables. Okay, this it changes the variables here. Okay, so it's summation all over the possible y minus x to the minus 1. I mean, sorry, I'm getting confused with the numbers and the letters. So so it's summation over all possible y minus 1 to the x dot. We get wait, I'm sorry, y minus 1 to the x dot y, and then we get y. All right, so we have Hadamard applied already on this qubit, in this gentle n qubit, and this n qubit, and variable x, and that gets basically it gets transformed here in the latter part in the in the right hand side. So it gets transformed into the summation over all y minus 1 to the x dot y1. Okay, so this expression now where we can see can be written as this one can be written as 1 over 2 to the n, where we have the summation over all x and summation over all y flip. Okay, and then we just move this minus 1 on the top to the f of x inside of it. Okay, so we'll try to expand this expression and then see how it gets the result that we want later. Okay, later on I'll just give it out, the expansion of this, but for now, since we only have limited time, we'll go faster. Okay, all right, so the last step here is we just all right. Okay. Can we skip on this? All right. Oh, no, can you go back? Ayan. Dyan pa rin tayo. All right, so the last step here is we measure the first n qubits. Okay, the first n qubits. So once we measure the first qubits, that's all about it. Okay, So if f is a constant function, then the measurement output will be all zeros. So it's 0 to the n, all n qubits will be measured to 0. Okay, so if it's not all zeros, that it's if it's not all 0, that is the output of any of all the bit is 1. All right, so then we can conclude that it's a balanced function. All right, but okay, so we will just derive how we arrived at this. Okay, so but yeah, that's all about it. But these are 4 steps that we need to do first in knowing the result of the Deutsch-Jost algorithm. First is to apply the Hadamard on all the input qubits, or even before that step. And then 0, we prepare and all 0 are the first 10 qubits to be 0 and the last qubit to be 1. Okay, so all right, so this is very okay, so let's try to focus on the expression that this expression right here in the bottommost part that can be written as this. Okay, so in particular, we'll focus on the one that's inside the brackets. Okay, so we'll prove in the next slide that this expression is, if we focus on in the all 0 state, if we focus on it, if we focus on the probability, this is a probability with respect to the with respect to this is with respect to all 0 to the all 0 of the state. Okay, so because we have 1/2 to the n, the summation of all over all y, this is, so basically if we focus on the probability for all the 0 state, we will see that if f is a constant function, the summation will be evaluated to 1. But if f is a balanced function, this summation, okay, this summation right here inside the bracket will always evaluate to 0 for all the 0 state. Okay, we'll just see this in the next slide. Okay, next slide, please. Okay, so this is the expression. This is the same expression basically. Okay, so inside the brackets. Okay, so since if we focus, since we are trying to focus on the all 0 state, we substitute y equals 0, right? So the dot product x dot y is 0 and -1 to the 0 is 1. So we get the next expression, which is equal to this. Okay, so for over all x minus 1 to the power f of x. Okay, all right, so we have here, try to look at this one, which if all right, so try to look at this one, the lower part of the first expression. So if f of x, if f is a constant function, f of x is always 0. All right, it's always 0, which means that it's summation all over x minus 1 to the 0 to the power 0, which means it's plus 2 to the n, right? Yeah, it's yeah, that's right. So, or if f of x is a constant 1, then it's -1 to the 1, which is -1. Okay, so essentially, if f of x is a constant function, then we can just move -1 to the f of x. Okay, no, we can write it as -1 to the f of x times 2 dot n 2, okay, to the n. All right, because there are 2 to the n possible values for x, and since f of x is a constant function, what that is independent of what the x will be, it's just -1 to the constant value times 2 to the n. Okay, So essentially, if f of x is a constant 0, it's plus 2 to the n. If okay, so if f of x is a constant 1 minus to the 2 to the n, but essentially it's plus yeah, sakto na de. Okay, but essentially it's plus or minus 2 to the n. Okay, so the modulus of it, it's always like 1. So let's say because we had this 1 over to the n. So the modulus of this probability for the all zero state is 1 if f of x is constant. All right. So next is if here in the balance, if what happens if f of x is balanced? If f of x is balanced for half of them, for 2 to the n divided by 2 of them, we'll have minus 1 to the power 0. Okay, because f of x is 0 for the other half of f is 1. So we have minus 1 to the power 1 times 2n by 2, I'm sorry. So the summation of this is 0. Okay, so for the all zero states, if f of x, if f of x is a balanced function, we get 0. And if x and then I'm sorry, if f is a constant function, we get 2 to the n divided by 2 there. All right. So that's basically just a summarized for the all zero states. So the probability of getting the zero state, which is this expression, the bottommost part expression, which is 1, if this only happens if and only if f is a constant. Okay, if it's a constant function. All right. In fact, it's more strong if it's 1, and then if f is a constant function and 0. If it's even something between 0 and 1, if it's 0, it's 0 if f is balanced. Okay, so basically this is what led us to claim the previous expression. Okay, so let's now proceed with the next slide, the Qiskit implementation. Javis, is it possible for you to share the composer? We'll just do uh, a quick right. Okay, so we'll just try to implement the circuit that we have that was presented. Okay, so we have to remember that the 4 steps, okay, that we have. Okay, so first step, step 0. Okay, step 0 is we'll place okay, all right. So first, let's apply. We'll choose. We'll have 3. Okay, we'll have Q0, Q1, Q2, and then Q3. All right, yun. All right, yan. Thank you, Javis. And then for the first register, since the point is 0, and then the last one to be 1 is Q1, so we'll apply okay, so this is by default already. So all right, I'm getting confused already. Okay, for a while. So let's apply a C0 gate, Jabez, in the last qubit, which is 3. Yan. All right. And then we apply a barrier after that from Q0 to Q3. So we can see that it's all 0, 0, 0, 0. Okay. So as we can see in the probabilities, it's all 0, 0, 0, 0. All right. So all right. Yeah. All right. So we added a barrier already. So basically, the barrier doesn't do anything. Okay, it's just for us to as we can see in the circuit that I've shown earlier in the presentation, there's a barrier. The red line, that's the barrier. Okay, so in this case, we have the barrier. So basically, the barrier doesn't do anything. It's just a physical representation. It has nothing to do with quantum algorithm execution. Okay, except that anything on the left is executed first, and then after one is the right hand side after the barrier. Okay, so it's sort of like partitions for the computation to face before the barrier. Okay, and after the value. But for now, for our understanding and the explanation of the algorithm, I'm just using a physical marker for to separate for it. Okay, so next step is we'll add a Hadamard for all of the qubits, right? Applying Hadamards. All right. All right. And Q3. All right. So as we can see, okay, and then we can add another barrier, Jabez, for after the Hadamard gates. Ayan. Ayan. So, right. So basically, we can see in the probabilities, we can easily see that we have already applied the Hadamard for all of them. We can see that it's already in an equal superposition for all the qubits. I mean, since there's a minus in the Q sphere, we can see that in the Q sphere, some of them have minus, and then we have phase associated with them. But for now, we can proceed so that we'll go on faster. So, okay, so so the next step is the implementation of the oracle. Okay, so in this case, the oracle is an abstract notion that we're using to separate differentiate the complexity of two algorithms or two classes of functions. And so all right, so we'll just skip it. Okay, so all right. So Jabez, can you place another C naught on can you place another C naught on the Q3? Yeah, all right. Ay, Jabez, can you take out the C nuts? Can you put the nut gate lang? Ayan. For both. Ayan, all right, all right. And then let's add another barrier for that. So we can see it's still evenly distributed. The probabilities are still even distributed from 0, 0, 0 to 1, 1, 1. So if it now we can still say if it's a constant or balanced function. Okay. So this is step one. We've already completed step one. We've added the nuts, and then we have already applied the Hadamards. And then we now applied another Hadamard gate from Q0 to Q3. No, until Q2. Yeah. All right. Thank you so much. Oh, all right. So we can now see, okay, we can now apply another barrier, Jabez. All right. Okay. So we can see now that the probability has already changed. Okay. So now we measure the first three qubits. We have Q0, Q1, and Q2. Okay. We now measure them. All right. All right. Looks cool, di ba? All right. It looks cool. We have, okay, so the final state that we get here. Now, notice that all of the probabilities are already in 0, 0, 0, 0. Okay. So for the first three qubits, the measurement is always 0. Okay. if yeah, all of the measurements is 0. I mean, it boils down to that state. Okay, so it's still in, as we can see in the Q sphere, it's still split into two. See, we have the 000, and then we have the 1000. All right. So this is because we haven't measured the last one. Okay. So that can be but we don't really care about it, since it's even though it's a part of a Deutsch-Jost algorithm, but here it says that it's always either 0. Okay. So with the probability of half, but we don't really care about it. So what we need is the first 3 qubits. Okay, that is 000, 000. Okay, it's always 000. Okay, so we can see the probability is already 100. So if we delete the X gate in the middle, if we try to delete the middle X gate, that one, so it's essentially it means that an oracle for a constant function for f equals 0, yeah, basically that's basically it. We can already, there's no changes actually. Okay, we can already infer here that this is a constant function for it. Okay, for the balanced function, all right, let's try to do the balanced function just for a quick one. Javis, can you apply 3 CNOT gates in the middle, yan, from Q3 until Q0. Sa baba, sa baba. Yun. Take that, tanggalin mo muna yung pinakataas. Yan, tas i-adjust mo yung ano, yung yan, all right, sige. And then move the barriers and the Hadamard gates. All right. And then adjust the first CNOT gate to its control to Q0. Yan. Yan. And then adjust the next CNOT gate and adjust it to Q1. All right. So now we can already say here that it's a it's about the same actually, even if we have the X gate. Okay, even if we apply any X gate into any qubits here, we'll get the same result to it. Okay, so this is a balanced function. All right, so hence the probability for all 0 states to occur is 0. All right, so that would be all for my part. You guys can try it out. Try to delve more on the circuits in Deutsch-Josa algorithm. Try to read more so that you'll get a better understanding of it. So basically, it's very confusing at first, but I know you'll get the hand of it. All right. So that would be all for my presentation. Thank you so much.
Awesome, awesome. Thank you very much for that, Lance. It might be a bit overwhelming at first, guys, especially for the notation. Pero yeah, what we basically do is uh parang i-front load natin ng work para kapag nag-run na siya, we can have like polynomial speed ups, 'di ba? So as Lance mentioned earlier, na if you try no inputting all the possibilities like 0000 tapos 0001, like if you do that classically, no, you would take exponential time, 'di ba? Pero if we use it, if we use this algorithm, 'di ba, na we can simplify it into polynomial time. So imagine how much time we can save if we have a large number of inputs, 'di ba? So ayun, it might yeah, I think it might be overwhelming at first, pero as you dive deep into it, you can see the elegance on the um implementation, and ang amazing lang paano nila naisip yung mga ganyan, 'di ba? So again, thank you very much, Lance, for that very wonderful talk about this very important algorithm in quantum computing, and even showing us in IBM Quantum. So yeah. Okay, so again, you can explore more, guys. No, just create an account on IBM Quantum Experience. No, you don't need to do anything. You don't need to pay anything. Just your email and such. Need you lang i-verify. And yeah, you can use that and you can visualize your circuit. Now, good. Okay, at this point, yeah, we still have a little bit more time. So let's jump right into our final session for tonight. No, yeah, without further ado, I would like to welcome Sir Dylan Josh Lopez. Hello po, sir.
Hi. So hi everyone. Hope you're still alive. Can I see some thumbs up or heart reacts if you're still here? Great. Okay. So I hope I won't bore you with the last topic since this is a bit of an overlap of a bit of advanced mathematics and physics. So allow me to share my screen. Oh, wait. Okay, let me share my screen. I'm going to talk about quantum optimization. So, most of you might think this is a boring topic, and well, it depends on how we would take it. But I'll try not to bore you with all of the mathematics with our topic today. So, quantum optimization. Why do we need to know about this? If you want to have a high-paying job and do quantum computing at the same time in the Philippines, you understand quantum optimization. Okay, this is something not just for mathematics, not just for computer science. This is something that you could use in industries as part of data science or artificial intelligence. So let me go right away. And what do we need to know about today? So I'm going to talk about optimization theory in a bit fast pace, in a nutshell. And then we're going to talk about some quantum computing and optimization. So I'm sorry in advance, I can't actually cover coding and quantum optimization today since I think we won't have enough time in doing it. But don't worry, I'll send a GitHub repo to everyone that will cover optimization and quantum computing at the same time. Right. So hope you're still here, and we'll get into optimization. So let me talk about the summary of optimization theory. Now, first question, what does it really mean to be optimized? Anyone here who wants to try? How can you say something is optimized? Is this something for those who have OCDs only? What do you think? Anyone? What do you what is the first word or sentence that comes into mind if you hear optimized? Something fast, something furious. Anyone, what do you think? What do you imagine when you hear optimized? Efficiency, that's correct. Maximum efficiency because everything needs to be right in line, right? Is it to be always correct? Something fast, okay? Less time and resources needed to accomplish the task. Something less? Great answers. And those are actually concepts that we need to take in when we do optimization because we want things to be optimized when we do optimization. So a very crude definition we could have is optimization is finding the best way of doing something. It's not necessarily less, not necessarily more. It depends on the problem that we need to have, okay? So let's put this in mind that optimization is finding the best way of doing something. Okay? Very friendly for everyone. And we're not going to bombard you with mathematical concepts right away. So in optimization, there's always pieces or ingredients that we need to have so that we can formulate something interesting or something impactful for everyone. First, we need a problem, right? We can't solve or optimize something if there's nothing to optimize. So we need to have a problem. Why do we need to be optimized? So one problem is, for example, I am a salesman and I want to travel all of the cities in the US with the shortest amount of time or shortest amount of distance to cover. Or I am going hiking tomorrow and I want to pack all of the stuff that I need for the travel while not being overcumbered. Okay. So those are the problems that I have right now, and probably something that you are facing right now as well. Now, if you have similar problems, then probably you are going to formulate an optimization problem in the future that could be optimized or automated by programming, algorithms, or even quantum computing. Now, given a problem, now we need to have an objective. How can we say something is optimized? Okay. So when we're trying to travel, are we going to travel? Are we going to visit less cities? Or are we going to cover all the cities with less distance covered? Or are we going to make it more? Like, do we need to have more time spending in each city? So we want to have our definition of optimization, or how do you define being optimized or being the best, or what is it to be efficient? So that's your definition. It could be a business concept, it could be a philosophical concept, or a mathematical concept. But in this case, it's mathematics. So we either take the minimum of something, the lowest something, or the biggest something. So for example, we want to optimize a process to maximize profit or minimize cost. So those two things are still objectives, but still we can put them in optimization. It doesn't have to be less. Sometimes it has to be the greatest thing within the scope. So in this first problem, if we're going to travel all of the states in America with the minimum amount of distance covered, then probably the optimization is based on distance. So we're going to compute using a distance formula. Cool, easy. Now, how about the bag? How can we pack everything in our bag with the most efficient way? Now, how can you say something is full? You can compute for its volume. So if you reach the certain volume of your bag, given the things that you're going to pack, then something could be efficiently packed within your bag. And you can also consider weight. Now, those are the main two things that you need to have if you want to form an optimization problem. However, there's another thing is, how can you be optimized? How do we optimize something? Do we suddenly, okay, it's optimized, it's just magically optimized? No, we need to find a way in how to do that. But let's define that later on. So next, I'm going to define some of the types of optimizations that you might be you're going to be encountering in the next few slides, or probably in the future. So take note, I'm not going to discuss everything about optimization. So we're going to pick the very few important ones for today. But the first one is parametric optimization. Okay, sounds very scary. Don't worry, it's not. When we talk about parametric optimization, we're talking about parameters. That means the optimization problem requires parameters. Now, if you see something like this in many papers or probably in books, it's most likely a parametric optimization when you have a specific objective function, and it is defined between bounds when there are constraints. Now, how do we read this? So first, when you see this min f of x, that means it's going to find the minima of a function, or let's say the optimization problem wants to find the lowest something of a certain function. So that's your objective. Now, there is an ST here. This means subject to. Now, these now are what we call constraints. That means the limitations of a certain problem. Now, there are what we call equality constraints, and there could be inequality constraints. Now, these might sound a bit mathematical. Let's try to go back into the real world. So let's have an example. Given that, let's put that into the side and let's try to give a real world example. So I want to find the cheapest way to eat for each day. Simple. That is actually an objective of an optimization problem. That is, again, objective. That means we are finding the cheapest way to eat for each day. So that's the minimum of spending given that you are eating something. But, oh, sorry, since my budget is limited, okay, here comes the constraints. I can only buy a total of 3 rice meals a day. All right. I'm sorry for you, but that's only 3 rice meals, no burgers. And I can only spend a total of 300 pesos a day at most. Okay. Now that's very strict, but that's okay. But that's his problem, not yours. Your problem is just to form an optimization problem. So when you're trying to translate this into mathematics, so this means we're trying to minimize the cost given the meals. So it is a function of cost given meals, right? So that's the objective. Easy. Subject to, that means since there are constraints, the total number of meals that you could eat should be a total of 3. Only 3. Could not be less, could not be more. Now, this upside down A means for all. It's what we call a universal operator. That means for all days. This means the English version, this is actually a translation. The sum of all meals for all of the days or for all of the meals that I have for all days should be free. Okay. Now, for the second one, second constraint talks about the cost of all meals that I'm going to have should not exceed, should be less than or equal to 300 for all of the days. Okay, so that's easy. Okay, so raise your hand if everything is still okay and not too scary. Okay, do not be afraid. Okay, cool. So now let's try to make this a bit more formal. So now we're just going to have it, with less words, but more variables now, and we're going to have a bit of definition on the side. Now, this is something that you would probably see in most books or papers that you are going to read or scientific blog posts. So that is parametric optimization. It's just very easy. It's just a translation of English to mathematics. Cool. Now, I'm going to head over to the next types of optimizations. We have what we call convex and non-convex optimization. Now these just talk about the objective function and how it looks like if you graph it. So a convex optimization is that when your optimization function or objective function is convex. Okay, that's okay, true. So this means if it's convex, it doesn't necessarily be a parabola. But if you try to draw a line for each point, for every part of let me see, can I draw something here? Highlighter. Wait. So if I draw one line or one line segment in any part of this graph, it should only intersect 2 points at a time. Okay, nothing, no free, only a straight line. So if it passed that test, it passes the convexity of your function. That is an opposite of the non-convex. So if I to draw a line from this point to this point, it actually hits along these curves. And that does not mean, that already defeats the definition of convexity. So that is a non-convex function. Now, there are some points here, literally points, that we have. So we have P1, that's what we call a local minima. P3 is a global minima. And P2 is a saddle point. Now, if you are doing machine learning, these might ring a bell. So, but for those who don't, this is the very vague idea about it. When you look at the function in a very bird's eye point of view, there is the lowest point, that is P3. That means that is the very smallest or the lowest point in the graph. That is the global minima. Then if there is another dip that is not the lowest point, but is a dip, that is a local minima. Now, if there is a line, almost straight line within the graph, that's called a saddle point. It's saddle point because it looks like the saddle of a horse if you draw it in a 2 or 3-dimensional graph. Okay, so this is an example as well of a non-convex function, right? So cool. That's just a very graphic way of defining convex and non-convex optimization. Now let's talk about how. How are we going to optimize these optimization problems? So we have what we call gradient-based optimization. I'm not going to go through in the depth of gradient-based optimization, but the key point here is we're computing for gradients. And we talk about gradients, these are derivatives. So we are doing multi-dimensional or multivariate calculus to find out where is the minima or maxima of a certain function. Now, take note that these graphs are the objective functions, okay? So if we're doing a minimization function or minimization optimization, we're finding the lowest point. But if we're doing a maximization problem, we're finding the highest point. Either way, you will also get what we call the zero gradient. I mean, if you find that their derivative is 0, that means you are in a minima or maxima. We don't know if it's a local or global minima or maxima. However, that's the point in gradient optimization. We use derivatives, right? Another one to solve this is what we call meta-heuristics. When you talk about meta-heuristics, we are simulating nature or a natural system or a physical system, and how do they correct themselves or how it is inspired to find out the answers themselves. This actually on the left side is what we call particle swarm optimization. It's based on swarm intelligence. One of them is like how do flocks of birds migrate or find food given a pack or given their flock. And here you might see this on TikTok or Instagram, is the slime mold optimization. Now there's fungi or that mold that tries to find certain nutrients and it spreads out like it has its own mind. Well, it does. And that's something that we're trying to mimic with algorithms so that we can find our own answers to objective problems or objective functions. Okay, so that's cool. So we're not going to dwell too deeply, and these are the only 5 things that you need to know so far with optimization for today. So in a summary, so the first 3, parametric, convex, and non-convex talks about the problem and the objective function. And then gradient-based optimization and meta-heuristic talks about how do we solve the optimization problem to find what is the optimized answer. Okay. Now, take note that even though the graph of a convex function or convex optimization is convex or simple, it's actually NP-hard. And these could be in the form of what we call mixed integer problems. And if we see an NP-hard, that rings a bell with quantum computing. So one of them is combinatorial optimization, also known as a mixed integer 1-0 problem, okay? So when we have this is by nature already an NP-hard problem. And this is something that quantum computing optimization really loves as a topic, okay? So classical computers would have problems when they're going to do combinatorial optimization. I mean, in this case, especially if you try to expand the case. Examples of combinatorial optimization are the knapsack problem, max cut problem, the traveling salesman problem. And there are other problems that does not not in the textbook, but would seem to be combinatorial problems when you try to formulate them in the real world, right? Cool. Now, optimization is hard, but it's okay. You don't have to understand everything at once right now, since this is a very complex topic. Now, if you do understand everything so far, that's great. You need to pat yourself on your back right now. Great. So I hope you're still with me. And now we're going to quantum. All right. So before we get into quantum, can I have a thumbs up? Raise your hand as long as you're alive. Hello. Right. Great. Hello. Hello. Great. Everybody still alive. Now, let me go to physics. Now, I want you to recall a bit of some classical mechanics, or just in general physics philosophy. The principle of minimum energy. That means every natural state of a physical entity would tend to find the minimum energy of things. Just like when you in a tired day would yearn for your bed, right? That's your minimum energy state. Or when you throw a ball up, it goes down. Or any type of energy system would tend to go down to its lowest state as possible, given its natural form, right? That's the principle of minimum energy. And that is innate in nature. And we can take advantage of that if we have a chance, right? So, this is an example of mapping out an energy state or a potential of a certain object or a particle, for example, right? So, there is a local energy minimum, there is a global energy minimum. Now, this looks very familiar to a certain problem. So this is actually looking like a non-convex problem, right? Or it could even be convex given a proper formulation. And gradient optimization would be very happy to solve these kinds of problems as well. But don't worry, meta-heuristics also does solve these problems. Now, given that this system looks like this, then is it an optimization problem? Is the universe solving a continuous optimization problem every day? That means that your system is, or you yourself is solving an optimization problem without even knowing it. And that is the law of nature. That means we are already doing optimization right now. Probably you are sleepy. Then that means that you are finding your own minimum energy right now. And you must recover that, right? So we can take advantage of that since it is a law of nature. It naturally happens. And do you think that this also happens in the quantum realm? Now, if it does, then we can take advantage as letting it flow with a quantum computer. Now, let's go back to physics. So, in classical mechanics, you can derive the total energy of a system as this. You have kinetic energy, you have potential energy. Now, for those who are in the physics, then you might know that this quantum mechanical form is the time-independent Schrödinger equation that also equates to an energy of a quantum object. Now, do not be afraid. Okay, we're not going to do any calculus with this, even though you see a double derivative right here. But this just means that there is energy computations in the quantum realm, and that means it may also tend to find the minimum energy in the natural state. So we could infer that in the quantum realm, that systems would tend to find its own optimal value given the chance that we set it properly. Okay, so that's amazing since we can just set a problem and let nature do it for us. And quantum mechanics could also help us do that. All right, well, I'm going to let you sink that in. But before that, here's the original Schrödinger equation, just for, shocking. So in all its glory, this is the original Schrödinger. I just want to show it to you. But yeah, actually, it will have a bearing later. So the left side actually talks about the time dependency of a Schrödinger equation, and the right side would tell you about just the space, and we don't care about the time much. And we could derive that later on. But in this case, it's just here. It's a display. So let's move on. I'm going to copy and paste this time-independent Schrödinger equation, and it would look like this. And I would just factor out this psi of x quantum object right here into the left side. And we're going to be left with this is actually just a constant with mass right here. And this is the position of a particle plus some v of x. And v of x is an energy potential of an object or quantum object, right? So An analogy would be something like this. Oh, something's wrong here. The kinetic energy is actually this h bar over negative 2m, right? That's kinetic energy, same as the total energy in classical mechanics. And this energy potential is, of course, the potential energy. So that means we are computing energy, and that's a proof that we are going to find something interesting if we let quantum mechanics solve a natural problem of energy. Okay, so I'm going to go back a bit here. So if we look at this parenthetical of the energy, what we call an Hamiltonian operator, and we call that this, and we just turn it into H, and it's a Hamiltonian operator, okay? So this is amazing. That means this H right here, this energy, actually this operator, is equivalent into finding a certain energy state of a problem, okay? Now you might be wondering, why am I talking about energy and where is the practicality of this? This is just physics, right? Don't worry, we're getting there. But another amazing fact is E here is actually just a number. And this H here is an operator or a linear transform, a matrix. So where did we see this? It's actually amazing. You can see this as a definition of the eigenvalue and eigenvector. So that means for some matrix H, there is some constant equivalent E. So it means there is an eigenvalue right here. And this is the eigenvector. It's amazing, right? So if you're not doing physics, you might try to learn it someday. So we can now use this as an idea in finding a global minima for an objective function. That's the method, but where's the problem, right? So we're going another side of physics is the Ising model, okay? So take note that we're talking about combinatorial problems. That means on and off. You're finding the right way of on and on switches and what gives the best effect. Now, the Ising model is a very cool model, okay? So given the configurations of these up and down arrows, these are actually ions or magnetic states that talks about pull up and pull down, okay? So in the problem here is that in what combinations of all of these magnetic poles that would give the lowest energy state of a certain object or matter. And that is already, in a sense, the objective function, or actually the problem of combinatorial optimization. The parameters are the orientations of the magnetic poles. And our task is to find what combinations would be good. And the objective is minimizing the energy. And that already is a good way to start an optimization problem. And given that we have a method already, that means we can do this in mathematics. So the Ising model is just like this. So let me just break down the math for you. This is the Hamiltonian of an Ising model, whereas J is the energy between all of these magnetic poles. And when we have this sigma I, sigma S, J rather, these are the interactions. For example, given this arrow right here, what are the interactions around it and interaction with across it? So it looks like what are the interactions of one particle to the rest of the world? Okay. And then we have H here would tell us about what are the external factors that would affect our one particle right here. And that's easy. And this could actually just be represented in a two-dimensional matrix. Okay, and that's easy, right? And take note that this sigma I here are just values between values either -1 and 1, either going up and going down. Another cool thing here is that you can form this as a graph. Since it's a matrix, it actually talks about what we call the adjacency matrix, because it talks about the interaction and what's the value itself. So we can see it something like this. So given a certain node of a graph, that is your sigma. And you can see that there are lines, these edges would pertain to the interactions of each of the nodes, represented by the strength of J. And this is now something amazing, since we can map this into an actual quantum computer architecture. And we're going to talk about that later. So cool. Now, there is another way. If you don't want negative ones and ones in your computation, there is what we call the quadratic unconstrained binary optimization. So if we have this in case of the Ising model, the Kubo model would just look like this. So you can see the only difference is that the values of the x's become 0 and 1, and this would now, well, they look actually just the same, just different values or different variables. So it's cool. So a bit seamless that we have transformed the idea of the Ising model to the Kubo model. So this now looks like more of a switching problem rather than a spinning problem or orientation problem. So you can imagine this more of the binary states of a certain thing. And you can do a lot of things with binary. You can represent a decimal number with binary, right? And that's amazing. Cool. Now, the objective function of a Kubo model would look like this. Now, don't be scared. This is just minimizing the whole Hamiltonian plus some penalty. Take note that we cannot write any constraints like greater than or equal here. We need to transform them in what we call penalties so that everything would be just in one function. That's why it is unconstrained. It doesn't mean that you can't put any constraints. It's just you can't write it explicitly as ST. You need to put them as penalties. Now, cool. We have a problem. We have an objective. Now let's talk about specific methods. Right. Cool. Now, let's talk about quantum optimization. In quantum optimization, let's go back a bit. Let's talk about quantum computers again. We want universal quantum computers. Mostly these are gate models. And the research I do is actually quantum annealers. And should I be sad? Actually, no. The trend would still be going to the universal quantum computer model. However, we have three main types that we need to consider when we're going to do the gate-based modeling. So there's measurement-based, there's topological, and adiabatic evolution or adiabatic computing. Now, good for those who are fans of the quantum annealers, that adiabatic computing is still considered part of the computation process of quantum annealing. Now, if you don't know what a quantum annealer is, it's a very specific type of quantum computer, that does only combinatorial optimization problems. So that's the only thing it could actually do. Think of it as a very specific microchip that does one thing, and that's optimization. But don't just say that it's just optimization. Optimization is a very important topic in industry. It could solve a lot of problems such as weather prediction, machine learning as well in other cases. It could be for economics, supply chain management, power management. So in that sense, if you have a specific device that does only optimization, then you can, if you are in the optimization field, or you are, another one is an industrial engineer, those who do operations research would be very happy because there's one specific computer that does only the thing, or specifically their job. Okay, so cool. Now, let's talk about quantum annealing, since that's a very specific topic right here in solving combinatorial optimization problems. Okay, so quantum annealing is still, there's still a sense of quantum computing here, wherein we're controlling the qubits using circulating currents or electromagnetism. Okay, and the way we start quantum annealing is, of course, we have a superposition state of the qubits, and we can represent that as this energy state right here. Okay, so once we try to do annealing, we are going to do what we call an evolution. We are going to decrease the temperature so that it could have, what we have here is a potential barrier, something that separates the 0 and 1. And that will slowly turn this superposition state from a quantum state to an observable classical state. So at the end of a quantum annealing process, we have classical measurements, all right? And the concept is what we call the adiabatic evolution. Now, those who have been studying thermodynamics might already heard the word adiabatic. And in this case, in adiabatic computing, we are slowly transitioning the problem to a micro problem to a macro problem. So here we have what we call H0. This is the Hamiltonian at the initial state. This small space right here. That's how we would initialize the problem. And S here is actually the constant for adiabatic evolution, wherein we try to increase this until such a value that H0 disappears, and the only thing that appears is the final Hamiltonian, which is what we call the problem Hamiltonian. This is the Kubo or Ising formula that we have. This would represent now the actual problem, the objective function that we have. And at the end of the adiabatic evolution, we would have a solution to our problem. Okay, so we usually start with superposition. Then as we increase the value of our S's, it collapses into these classical states. Now, these lines, they are actually couplers, and they entangle all of the values in between. Okay, so all of these qubits will now have specific values, and the strength of these interactions would be enhanced by couplers by entanglement. Cool, right? But that is quantum annealing. What's the problem? In quantum annealing, we don't have error correction. So we just create a lot of qubits right here, we prepare it, and we let nature flow. Just like I told you, this is the law of minimum energy, or the principle of minimum energy, right? So in that case, it doesn't have that much of a constraint. We don't have much control in how the qubits would interact or flow with nature. But we need to, right? If we want to have very specific and very accurate predictions or optimization values, we need to control that. So there is still a lot room of error for quantum annealing. So we need to be very careful, or we need to have a large enough problem or a medium enough problem so that it would be large enough for complexity that's subjective to noise, or small enough that, you know, a classical computer could actually solve easily. All right. So how do we solve this? So then we go back to universal quantum computers. So how do we integrate this in the gate-based computing? We have what we call the quantum approximate optimization algorithm, or QAOA. If you've heard of it, that's great. But how does it work? Let's talk about that. So it starts with a superposition state, and there is this series of parametric operations, these unitaries, that would lead us to a value, or this quantum object that has beta and gamma. This is actually the solved problem. This is the optimized state. This is the lowest state, or the optimized state of the Hamiltonian. So this U gamma is actually this problem unitary. This is the gate representation of the Ising model or Kubo model that represents our objective function. Oops, sorry. And the mixer unitary represents the initial state of our problem, right? Initial state of the Hamiltonian. So in this case, it's very easy to understand, and it's the same as how we would solve it with a quantum annealer. But what's the difference? We're using gates. And when we talk about gates, we are doing digital computing. That means we have a very limited number of qubits to use. Unlike in quantum annealing, you can use 5,000 qubits, but not in this case. We are very limited in number of qubits for a universal quantum computer. Advantage is we have a very stable, or we have a lot of quality qubits instead of 5,000 noisy qubits, okay? So in this case, we call these the problem Hamiltonian and the mixer Hamiltonian. Now, here comes the original Schrödinger equation again. And now we're going to look at the left side instead of the right side before. Now, this actually talks about the evolution, or the time evolution of a quantum object. That means okay, don't be scared, that this is just the change of the quantum state through time, is equivalent to some Hamiltonian acting on a certain quantum state, right? And if we do some math, we can actually find out that the quantum state would be equivalent to this operator times the initial state of this the first quantum state, right? That's easy. Okay, don't have nothing much there. Now, another problem is that in adiabatic evolution in quantum annealers, we assume a lot of spaces. That means there's a lot of value points that we can go through. However, in parameter, not parameter, in gate-based modeling, we are very limited with the number of information that we could hold. Okay, and this is actually a resolution problem. So if we represent this line right here, a very good line, that's 1,000 points. But can we represent it with lesser number of points so that we have a tolerable representation of this function still? So maybe 10 points would be enough. 5 points might be too bad. 15 is okay. So either of the two, we can use this as an idea of approximation. Since for those who are in engineering, this is actually sampling, right? To what value or to what level of downsampling can we subject our signal so that it would retain some or the least amount of error still? Okay. So how do we do that? So we're going to try to look at evolution once more. And this is actually what we call trotterization, the principle of trotterization in this case. So we have our time evolution Schrodinger again right here. Now it just states from our original state, okay, given this, if we try to just evolve this with next states, we could actually find a stepwise evolution of a quantum state. Ta-da. And it could lead us to here. And this could be discretized steps instead of having a very continuous, smooth adiabatic evolution. We can have this simulated evolution in terms of gate operations. And this still is evolution. And that is the guiding principle of QAOA. So given this, we can now just represent these unitaries as these. So these would be unitaries acting upon the final Hamiltonian and the initial Hamiltonian. So we can just combine them together, okay? And it will form something like this. So it's just the operations stacked upon each other until we get the final state. So we try to optimize all of these values using a classical optimizer. So in a sense, this is a variational quantum algorithm. So instead of using a time evolution, we're actually finding the right parameters of rotation gates, right? So I'm going to wrap it right here since we can't do any code. So quantum optimization could be done in two ways: quantum annealing or QAOA. Those are two main ways that we could do it right now. In quantum annealing, it's not universal, and it uses an initial and final Hamiltonian. It uses adiabatic evolution, and it's not really robust to noise. However, we can use a lot of qubits. In QAOA is it's gate-based model, so it's good for universal quantum computing. So the terms are just mixed. It just uses mixer and problem Hamiltonian instead of initial and final. So it simulates adiabatic evolution using trotterization. Okay, so in this case, we are trying to downsample the adiabatic process while retaining the efficiency. And it is a variational quantum algorithm. Now, sorry, again, we can't do any code right now. We can do a simulation of how do we set a problem. So I'm going to show you this slide. You can take a picture, since this is a guiding principle of how do we actually map or do the optimization. You start with a problem, make a formulation, make it a graph, and we send it to a quantum suite. So it could be D-Wave for quantum annealing. You can use Penny-Lane, Qiskit, or NVIDIA Quantum for simulating your QAOA. Now, if you want to do classical, you can use all of the existing suites right here. So I'm just going to go through an example of how do we do this in practicality. So say, for example, I'm going to do a cell tower placement problem. Let's say I'm PLDT, Globe, or Smart, and I want to set cell towers in 2025, okay, given the data that I have here. So I need to set up a plan. And how do I add more towers with efficiency? Say, for example, have free tower plans, 0, 1, 2, and 3, and that towers would cover these cities given in 1, okay? So I want to maximize the coverage of my cell sites with all of the cities, or as much as possible, every city right here, okay? So classically, I would say I want to maximize the covered city given the population, something like this. In Kubo, we tell it like this. So the difference here is instead of maximization, we need to minimize since principle of minimum energy wants to be minimum. So we use what we call the dual of an objective. So the maximization is just the equivalent this is the negative minimization, or rather the other way around. The minimization problem is the negative maximization objective. Okay. So that's the first thing. I want to cover every city. Next, I want to build every tower so that it would cover every city. Okay. So we can tell it like this. And in Kubo, we do it like this. So instead of doing a constraint, take note that there's no inequalities right here. We turn it into a penalty. So we just move it aside, move everything to the left side, and we need to square it in the most cases. Okay. And last constraint is that for every cost of the tower I build, it should be within my budget. So we can do it like this. And in the Kubo form, we can do it like this. Now, once you have everything, this could now actually constitute to your final Hamiltonian. And that will be now your Q, which is your objective function, plus your penalties right here, which are your constraints. Don't worry, lambdas are just coefficients or weights of how important these penalties are. Now, once you have this, you can now put it in your program and run it in Qiskit. You can run it in D-Wave, or you get other simulators. So that is a very, very brief overview of quantum optimization. I hope you like it, and thank you.
Awesome. Thank you very much for Sir Dylan for that very comprehensive yet very beginner-friendly introduction to optimization and even some applications on how we can use quantum computing so we can speed up those optimizations and hopefully we can solve problems faster and we can better contribute to society. 'Di ba? Yun naman ang pinaka ano doon, 'di ba? So we do have a lot of big problems. And using these techniques now, using quantum computing, hopefully we can solve those things faster, can solve more problems to better help the society. Okay, so right. Okay, so we're now opening. Sorry, we're a bit over time. We're a lot more over time. But yeah, we're opening the floor, the group chat now here in Zoom for questions so far. Ayan. So for the whole duration since October 14 to up until now. Do you have any questions, guys, that are still there are still concepts that are still unclear to you? Okay, so we'll have a few minutes for that. Yeah, just send them. I know nagta-type na kayo dyan. And yeah, we will answer them. And if hindi naman ma-answer for tonight, for the interest of time, we will download the chat for now and send you an answer through Discord naman. Okay? So yeah, uh yeah, I'm not seeing a question yet. So yeah, for now, no, just type your questions. Yeah, let me just discuss the certificates for now. Okay. Okay, so for your certificates, guys, to qualify for a certificate, dalawa yung certificates natin, certificate of participation and a completion certificate. No, so for the participation first, you need to complete the onboarding checklist. It was sent on your emails and attend at least 4 out of 6 of our lecture sessions, and of course, complete the offboarding checklist. Ayan. So don't worry, guys. If you're unsure if you've accomplished the things na nasa onboarding checklist, we will send it again no, complete siya with all of your standing so far. And as for the certificate of completion, as usual, onboarding checklist, 4 out of 6 sessions of boarding checklist. But this time, you need to accomplish all the exercises, no? So tatlo na yung nakapost. We'll post the last homework 4, and you need to get at least 60% on every requirement. Note that the certificate of completion is an authenticated e-certificate, no? It's something na meron siyang code and such na pwede mong i-check yung authenticity on the internet. The participation would be a PDF, no, that will be sent on your emails. Of course, yeah, life gets busy, so we do have some considerations. So yeah, we will send all your standing so far. So if you see na you just for you know that you attended but you forgot to send in the attendance form, no, you can send proofs of attendance. We can talk about it. And also, yeah, if we see na um there are not a lot of people that are doing well on some homeworks, particularly the second one, no, we can send some remedial homeworks for you. So you can message me, you can DM me on Discord or send an email to this email, jabez.ison@qcsp.ph. And lastly, ayan ba, mayroon ng question. So before going that confirmation emails, the information about your standings will be sent next week sa Tuesday. Ayan, so homework would be on Monday, and then sa Tuesday would be your standing email. So nandun yung scores nyo on our activities or homework so far, the status of your forms if you have submitted those forms, and your attendance, and of course the offboarding and the forms for the offboarding. And then yeah, the certificates will be sent 1 to 2 weeks afterwards. Okay. All right. So yeah, we do have a question. Since quantum computers, as I understood, are non-deterministic, does this mean that we can utilize them better for algorithms that employ randomization? For example, simulated annealing instead of something like this deterministic like addition. So Sir Brian answered correct. You can add with a quantum computer, but it is remarkably inefficient. The power of quantum computation comes from superposition and entanglement. Yeah, okay. I won't add anything. That's the most uh juicy and golden liquid, I should say, answer to that question. So yeah, if you do have some more, yeah, just send them out. For now, yeah, we ask everyone to please turn on your cameras for our photo op. Okay, hello, hello. Hi guys. Hello po. Ayan, good evening, good evening. It's already 8 p.m. Sorry for the delay. But yeah, we're very happy that you've been with us since the beginning, since October 14. Okay? Ayan. Hello, hello. Ayan, sige, sige. Okay, hello. Ayan, meron pa atang nasa labas. So, ingat po kayo. Yung mga nasa labas pa. Okay. Alright, so let me take a photo. For those now that can turn on your cameras, you can send in a reaction, heart reacts, so that we can feel your presence. Okay, taking the first slide, first page, 1, 2, 3, smile. Okay. Then for the next one, 1, 2, 3, smile. Okay. Alright. Wait, let me just share my screen again. Okay, so yeah, that's it for tonight. Yeah, although this is the last lecture, no, although this is the last lecture, we hope that you still keep in touch with us, no. Hindi dito matatapos ang inyong quantum journey. Now you can always send a message on Discord or send us an email if you have some questions, or even if you want to pursue or to do some computations or access hardware yourself. No, we are very open and we're here to help you out. Okay, so at this point, I would like to call on Sir Bobby.
Yeah, thank you very much, Jabez. Sorry, I cannot turn on my camera because I'm not feeling so well. But yeah, so this first lecture series was really geared towards the hackathon, and I think that we have accomplished our goal. No, the goal really was for you to be able to first have a like an overview of quantum computing in its different aspects, like for example, optimization, cryptography, and the algorithms. And the second important goal really was for you to be able to create quantum circuits, no? Which you have demonstrated to a very outstanding degree, no? In the hackathon. So really congratulations for everyone. No? I did not I did not really expect that you will finish that, no? But I was so surprised that uh, two groups really finished the all of the all of the questions, all of the challenges. So very congratulations, no? Tapos yung iba hindi nagkakalayo, no? They some of them were not able to answer three, some were not able to answer two, no? So it's a very close competition. But at the end of the day, no, the thing is, you know already how to create quantum circuits, no, just by giving you a specification. So that's the basic thing, no? And the next thing that we will do is to dig deeper into the quantum algorithms, no? Like for example, the Deutsche-Joshua algorithm, no? Shor's algorithm, Grover's algorithm. These are a topic of lecture series number 2, no? which which the group in One Quantum will plan to give, no? So so stay tuned, no? Stay tuned. We will definitely uh, run lecture series number 2, which builds on top of the lecture series number 1. Yeah, so I think that's it for me, Javis.
Awesome. Thank you, sir. All right. Okay, at this point, yeah, again very thankful for staying with us up until now. So yeah, for the last attendance for the first lecture series, yeah, here it is. Ayan, to close in an hour. So please yeah, accomplish that bago kayo kumain. And then yeah. Okay. At this point, yeah, if you're finished on the form already, you can leave the call. Otherwise, you can stay and enjoy some music. Again, we're very thankful for everyone. If you have some questions, please get in touch. No, we want to equip you guys with the tools that you need and knowledge that you need to build and use quantum computing. All right. Thank you, everyone. Bye bye. Thank you. Thank you.